Hello, my name is Wil van der Aalst and it's a great pleasure to give this talk on object-centric process mining. The goal of object-centric process mining is to bridge the gap between data as we find it in information systems and processes as they are really being executed, and the event logs that serve as input for process mining tools. We will see that reality is often much more complicated than what people think if they look at a simple BPMN diagram or some flowchart or a directly follows graph generated with a process mining tool. I will show that reality is more difficult, but at the same time there is a lot of potential of analyzing processes as they really are. So to start, I would like to show this quote that I think many of you know. It was said by Albert Einstein, who said everything should be made as simple as possible, but no simpler. And often if we try to do process mining based on real information systems, so for example an SAP installation with tens of thousands of tables, we are trying to make things too simple. We think that it is easy to capture what is happening in a process in a simple XES log, simple event log, and I will show that this is actually more tricky, but there is the potential to solve a lot of problems by simply acknowledging the fact that there is no such thing as a single case ID and that you are actually dealing with interacting objects. What I mean exactly by this will become clear in a second. Okay, let's provide a high-level overview of process mining. This is not a talk explaining process mining from scratch, but I simply need to set the scene. So process mining starts by extracting event data from information systems. One is able to explore, select, filter, clean such event data. Then we can automatically generate process models. For people that have never seen this, let's say live, this is often astonishing. It is often described as seeing snow for the first time in your entire life. The same effect you have if people are shown the processes that they are actually involved in, and they can see things that they could never see before. But of course process mining doesn't stop here. One can use these models either as they are discovered or as they are made by hand, and one can combine that with event data. We call that replaying the event data on top of these models, and by doing that we can see where there are deviations from a normative model, or if we have a discovered model showing, let's say, the mainstream behavior, we can see all the infrequent outlier behavior. So we can see conformance and compliance diagnostics, and we can see bottlenecks. And so we can see where in the process are the biggest skews and what is causing them. Then what is the connection between process mining and things like machine learning and artificial intelligence? That comes in the last step in this diagram, where we are using these models which are discovered and enriched with the event data that we have. We can generate models that are predictive, so they can be used for example, to generate recommendations of what are the best things to be done. One can use neural networks or any other machine learning technique then to make such predictions. This last step is actually quite easy. The main contribution of process mining is in these first two steps that we see here. Of course, the goal is not just to generate diagnostics. So process mining is providing you, let's say, information and sometimes automated actions to actually improve the process. So for example, if you see that in a particular process there is a lot of rework, you can diagnose what is causing that rework, and then you can take the corresponding actions, either by redesigning the process or by automatically triggering let's say, mini workflows that address the problem that you have seen. So that's a high-level view of the field. I started to work on process mining in the late 90s. Let's say my group in Eindhoven was the first group to really, let's say, focus on this particular problem. In the beginning, it was very much an academic exercise. We developed many algorithms, and still many of the capabilities that you see in today's process mining tools are based on ideas, let's say, developed from the late 90s to let's say, the year 2005. And so things like conformance checking, decision mining, generating these types of predictions all existed before. Then, let's say, a bit more than a decade ago, commercial tools start to appear based on the ideas that we had worked on. Initially, these tools were not very visible, also not so super successful. But what we see in recent years is that many more process mining vendors appeared, and more important, the adoption in industry has increased very rapidly. And so now in some countries like Germany and the Netherlands, you can see that process mining is slowly becoming the normal thing to do, not something exceptional. So this shows the timeline of the field. There are currently over 30 commercial process mining tools available. You see some of them on this slide. In the academic world, of course, we also developed a lot of open source software. So, for example, I worked on software like the PROM, but also more recent developments like PM4Pi. But there are also, for example, initiatives based on R, etc., etc. So there are many tools available, and these tools need as input an event log. And now I come to the topic of this talk. Once you have the event log, process mining is actually very simple and doesn't take a lot of time. The painful process is often in extracting the data. For example, if people ask, okay, can you mine SAP data? Yes, of course you can. But there is still a lot of work to be done, because for a particular process you need to identify what are the tables relevant for that process, and then you need to extract them. And even for super standard processes like the purchase to pay process, this extraction process may be very complicated. And we will find out why that is the case. So on the one hand, there is this, let's say, complex reality with thousands of tables, and sometimes we are dealing with also with thousands of different attributes in all of these tables. And a prime example would be SAP. And then we would like to create a so-called event log, for example, in XCS format. So XCS is the IEEE standard for storing event data. And this feels like pushing an elephant through a keyhole, because from, let's say, this environment with many tables, many attributes, describing many different types of objects, we need to come to this standardized input format, which is very powerful, but at the same time also a bit restrictive. So this was top down. Now I go bottom up, and I'm going to first talk about what is traditional process mining, and then show how object-centric process mining is extending this. So if we look at raw, plain event data, then you can think of an event as something that has happened in reality. This can be represented by, for example, a record in a table or a row in a spreadsheet, as you can see here. Every event, so every row, can have an arbitrary number of attributes. But the minimal requirement for process mining is that for every event we know at least the case identifier, the activity, and the timestamp. So these are three mandatory attributes of an event. We can use all this other information, so information about costs, quantities, locations, machines, resources, etc. But the starting point, as I showed in the overview diagram, is an event log that has this, let's say, minimal information. So timestamp is obvious, activity is also obvious, like in this order handling process. This is placing an order, making a payment, sending an invoice, and these types of things. And of course, these things are related to something, and this something in this example is an order. And in this very simplistic example, my case identifier is the order number. If you would go to a hospital and you would look at different tables in healthcare information system, then one will often see that the case ID is, for example, the patient number. If you go to something like an airport and you look at the baggage handling process, then the timestamp is obvious. The activity may be, for example, that the bag is being scanned, or a bag is being checked in, or a bag is being stored, or the bag passes a certain sensor. And the case identifier is the identification of that particular bag or suitcase. So now that we understand event data, it's easy to understand that we can convert the data that I was showing here to sequences of activities where every sequence relates to one of the cases in our data set. So in the table that I just showed, I was just showing a tiny fragment. In total, there are over 12,000 cases. And here you see, let's say, how these cases are composed. So, for example, 8,000 cases, in this example orders, follow this sequence of activities. Place order, send invoice, pay, prepare delivery, make delivery, confirm payment. There are more than 1,600 cancellations that have followed this pattern of these three activities. If we look at the blue set of cases that all follow this trace or this pattern, we see that they are very much the same as the first one. The only thing that we see is that the last two activities are being swapped. And there are these 37 exceptional cases where people have paid before they got an invoice. But for the rest, they are similar to the blue and the green variant. So using such data, as I mentioned before, some people that see this for the first time, the experience is similar to seeing snow for the first time. Using such very simple data that you can find everywhere, you can automatically generate process models. These process models show what are the highways, what are the infrequent paths. These process models can also show where the bottlenecks are, and we can overlay these models with a lot of information. And that's often very surprising because this is not subjective, it's based on the data, and it reveals often things that people would normally not see. So why is this useful from a practical point of view? This is useful to find out what really happens. This information is very powerful because people that see these diagrams immediately see how things can be improved. It can be used to identify and to diagnose bottlenecks. Where are the main bottlenecks and what is causing them? And we can also indicate if we have a normative model where the process is deviating from what is specified. If we don't have a normative model, we can generate a model that is describing the, let's say, the most typical behavior, and then we can highlight the deviations. That's what I did here, and here you nicely see the 37 cases where people have paid before they got the invoice, and then there this send invoice activity is being skipped. So we see performance diagnostic, we see conformance diagnostics, and these models can be used in a predictive setting. So So this is all great. This is all, let's say, proven technology. It's something that you can use today. However, the main assumption of everything that I've shown so far is that there is a clear case identifier. So normally you don't think about process models in such a way because you just see, let's say, sequences of activities. But if you're drawing, for example, a BPMN model or any other notation that you may like, implicitly there is a case notion, because the process model is describing how you're handling one case in isolation. So this notion will be in BPMN, in UML activity diagrams, in event-driven process chains, in workflow nets, a special variant of Petri nets. No matter what you take, you need something like this. So that is the traditional setting. As I said, proven technology, but it has this requirement that I ended with. Now we look at the real world, and I'm going to show you that this assumption that seemed completely logical is actually very limiting and sometimes leading to very confusing results. So here I'm showing a small process related to a company like Amazon. It's an abstract example, but you can keep that in mind. On a particular day, so for example Black Friday or Cyber Monday, I can go to the Amazon website and I can place an order. Maybe I place not just a single order, I can place multiple orders. If I look at one order, then one order is composed possibly of multiple items. There is at least one item, but an order may be composed also, for example, of 10 items. So here in my order there are these 3 great books and there is this iPhone. Then these items are shipped to my home. And if I order multiple items, it could be that there are packages that contain multiple items. To complicate matters, it could be that part of my order is in stock, the other part is not. So it could be that some of the items that I've ordered end up in a package. But other parts of the order end up in different packages. Moreover, in the same package, suppose that on Black Friday I place 10 times an order of 4 items, it could be that packages contain items of very different orders. Then after these packages have been created, they of course need to be sent to my home. And it may be the case that I'm not at home. And if the package is valuable, it cannot simply be left. So these delivery attempts are on a so-called route. And on a route, of course, we typically deliver many different packages, but the same package may be on different routes. So this is sketching, let's say, reality, and if you would look at tables in SAP, these are the typical structures that you see. For example, if I look at the relationship between an order and a package, that is a many-to-many relationship, because one order may be split over multiple packages and one package may contain items of different orders. So here it is very difficult to imagine what the case identifier would be. We can make order, case identifier, item, package or route, but it all leads to problems, as we will see in a minute. Just to describe what I was just talking about at an instance level, so that this image is very clear to you. Here I have an abstract order 1 that consists of 3 items. And 2 items of order 1 end up in package 1, but package 1 also contains an item from order 2. So what we see is order 2 has things in package 1 and package 2. Order 2 has things in package 1 and package 3. Also package 3 has again items from 2 different orders, so in this example order 2 and order 3. So here you can see the complexity of things. So orders, items, packages, routes are all different things. And some of the activities that we see are just referring to one of these entities, one of these objects, but sometimes also to multiple. And so for example, if we place an order, that refers to one order and possibly multiple items. But if I check the availability, when I'm, for example, preparing for order picking, then I'm checking things at an item level. And then if we try to deliver things, that is at the level of a package. So there are all these different objects, and activities may refer to different types of objects. So for example, if we are packing items in a package, it may relate multiple items to a single package. So let's now, because this is reality, this is the complexity that we deal with, let's now assume that rather than having a traditional event log, like for example the XCS format or a simple CSV file, we make it one step more realistic, and we assume that instead of a case ID, we can have any number of objects related to an event. So an event is an activity, a timestamp, any set of objects and attributes. So if I highlight that, we have the activity column, we have the timestamp column, just as before. Events may have any number of attributes, like for example price and weight. An event no longer has a case identifier, but an event may refer to any number of objects, and these objects can be of different types. So we have order, items, packages, customers, and products as the different types. And what is important is that there can be many different types of objects. So normally we would have a separate column to, for example, represent the resource involved. A resource is just a type of object. But we can also have locations, we can have customers, all kinds of things are possible. So this is a generalization of the notion of case, resource, and many of the things that you would normally load into a process mining tool. So objects are the key element. An event may refer to any number of objects. So just to highlight some examples, so here we have an event place order, and place order is referring to one order and multiple items. So this was an order consisting of 2 items. If we look at the pick item event, then it is referring to just a single item. If we think of a failed delivery, then that is referring to a package, and the package that we attempted to deliver but nobody was home, and this package may contain different types of items, as you can see here. So now we have this data. You can see it's kind of in between the actual tables in the information system and the normal event log format. But now we have this intermediate format, and we would like to load it in your favorite process mining tool. And how to do that? Well, we need a case ID in order to load it into the tool, and we have also seen that things like BPMN are in essence assuming that you have such a single case notion. So how to do this? And this is what people are doing implicitly when they are writing SQL queries on database tables to extract an event log. Here I'm doing that explicitly based on the intermediate format of an object-centric event log that I just introduced. So what we do is we need to pick a case notion if we want to bring it to traditional process mining. And then if that's basically picking a particular column, and then given that column, we replicate the event for each object that appears in that column attached to such an event. So it's best to give an example. If we make orders our case ID, then this was one event and it will remain one event. If we make items our case ID, this row, which in reality is one event, is replicated because we have an event for this item and we have an event for that item. If we would take packages as our case identifier, then this event would disappear because it is not related to any package. So let's show this visually. So if I take order as a case notion, then if there is just one order related to a particular event, nothing much changes. But if an event refers to multiple orders, this event is replicated for each of these orders. So we see that this event is transformed into two events related to the two different orders. If we take items as a case ID, the same principle. So place order refers to two items. So we have two events corresponding to this single original event. If you look at this send package event, we can actually see that there are three new events related to that original event because that send package contains three items, as you can see here. So we are replicating events. What can also happen is that things disappear. So if an event is not referring to objects of a particular type, and we take that object type as our case notion, then of course these things disappear. So what have we seen now? In the latter case, we saw a potential problem that we call deficiency, and that means that events are disappearing because we focus on a particular type of object, and we basically lose all the events that do not directly refer to one or more of such objects. The other problem is convergence. So we have events referring to multiple objects, we just saw that, where we are replicating things, and this may lead to, let's say, confusing diagnostics because our numbers are no longer correct. I will explain this in a minute. The last problem is divergence. This is often the cause for spaghetti models, as we call them. And here the problem is that we choose a particular case notion, and because of that case notion, events are taken together, also events which are not directly related to each other. It's best to explain convergence and divergence using the example that I introduced before. So if we are taking items as a case identifier, we are replicating these events, and that leads to the potential problem that events are, in this case, there are three events referring to the same original event. If we now attach costs to it, or we attach, let's say, delays to it, we are getting very misleading diagnostics because this event happened only once and it is there three times. So we should be careful that if we do some cost computation, that not suddenly we count this event three times. Also, if we think about waiting times, it becomes, let's say, undefined what waiting times really are if it refers to multiple objects. Then there is a problem of divergence that is more complicated. So here I picked order as my case identifier, and at first glance this looks very good because in this particular example every event refers to only one order, so we are not duplicating things. However, please take a look at the items column, and we see that in our data for every item we first see place order followed by pick item followed by pack item, and then it ends. And we can see that for every item there is a very clear order. However, if we apply process mining, we forget about the fact that there are these items, this is what we see. So for every item, we see the sequence place order, pick item, pack item. But because we are using orders as a case identifier, we now suddenly see all kinds of connections here that do not exist at item level. So for example, in our data, we see, for example, that pick item is followed by pick item. That is this arc. Or pack item is followed by pack item. That is this connection. Or pack item is followed by pick item. That is backwards error. So all of these connections are there, they happen, but it's very, let's say, disturbing, because this process model allows for many more things than what we just see, because the causality among items is lost. So what we would really like to see is something like this, where we first execute place order, and then for each of these items, we see the sequence pick item, pack item. So this is the reason why often process models tend to be complicated. This is caused by discovery techniques not being able to handle concurrency. So if things do not happen in a fixed order, immediately all kinds of loops are created. And this divergence problem, of course, makes that much worse, because connections between, let's say, unrelated events are shown in the corresponding process model. So you may think this all sounds very academic and very abstract, but this is actually a major problem for anybody that has been doing, let's say, process mining in the real world. Because if you look at the database schema, here you see in a few in the notations, the situation at the bottom is very rare. So for example, if I look, for example, at this data model from a hospital, what you see is almost all the relationships are one-to-many or many-to-many. Having a one-to-one relationship is actually something that is very rare. So in every application where you are dealing with multiple tables that have timestamps in them, this problem exists. And a single case notion is not enough to capture this in a proper way. Okay, so how can we handle this? Well, this slide is indicating 3 levels. So what is tagged here as the mild level is the way that most organizations are doing it now. While extracting the data from the information system, these divergence and convergence problems are implicitly created. And you don't see them anymore if you look at the event data. A better solution would be to store the event data in an intermediate format, which we call object-centric event logs. This is something that you can already do today using existing technologies. And then each time you want to do process mining, you choose a particular view, you choose a particular case notion, and when doing that, you are aware of the fact that you may introduce these convergence or divergence problems. And that is not a problem as long as you know, and as long as you can have multiple views. So you can mine a process at the order level, or you can mine a process at the item level, and you will generate different process models that have their limitations. The most ambitious solution, and something that we are working on in our research, is what is called here the hot level, where we don't try to discover conventional process models, because this is impossible for this more complicated reality. And we generate automatically models that capture what we are doing. So this is showing this visually. So the classical approach is that each time we want to create a process model from event data, we need to have a different abstraction. So for every view, we need to to go back to our original information system and do the extraction. That is time consuming and may also lead to let's say confusion, because how this is exactly extracted also influences, for example, the frequencies and the times that you see in the diagram. A much better approach is to, from this information system, first store the data in an object-centric event log where you are not forced to choose a single case identifier, and then on demand from this object-centric event log you generate conventional event logs that have the problems that I mentioned before, but you know with every view that you generate what the underlying assumptions are. And you know that in a particular view you should interpret numbers in a particular way. The most ambitious solution is that based on these object-centric event logs, you don't pick a case notion, also not on demand, but you immediately generate a much more holistic process model, which is showing the different object flows all in one diagram. So it goes too far to explain this in detail. I will provide pointers in a few minutes. But this is what it looks like. So we load an object-centric event log, and we automatically generate a model that is capturing the different types of objects. So in this diagram, what we see is we see the items, that is the red flow. We see the orders, that is the green flow. And we see the packages, that is the purple flow. And if there is one thing that you should remember from what I'm showing here, if in the models that we discover in this way, if you see a certain number, you know it is right. So for example here, package delivered 1296, we know that this event happened exactly this number of times. If I would have flattened the log before, there could be a frequency which is much higher because I should interpret this at the item level. There are, let's say, there are thick arcs and let's say these normal arcs. In a normal arc, like there is one object involved. If there is such a thick arc, that corresponds to the fact that there could be multiple objects involved in the corresponding activity. So for example, here, package delivered refers to one package, but may involve, let's say, any number of items in that particular package. So how does this work technically? I'm not going to explain the details, but the principle is quite easy. We first flatten the event log for each possible case notion. So for every object type, we create a model, but these models have these convergence and divergence problems that I mentioned before. Then we see how every object is flowing through the corresponding process model, and we do this separately for every object type. And so here I have three object types, order, item, and route, and I treat them separately. What you now see is that at the item level, place order was happening 500 times. At the order level, it is happening only 100 times. If I look at start route, and at the route level, there are just 10 routes. And then there is 10. If we look at it at the item level, there are 500. So we first do this, and like in isolation, they are correct. And then I merge these models. But while doing that, I ensure that the numbers are correct. And the way to do that is that I bring back the frequency of every activity to the real frequency as it was in the log. And we can have these, let's say, traditional arcs that just consume one and produce one object. And there are these, let's say, thicker arcs where a collection of objects can go in and go out. So that's the basic idea, and this slide is showing, let's say, in a bit more detail how this works. So for example, if we look at place order happened 100 times, and this is the item flow. So earlier it said 500 for place order, but in reality it's only 100. So we know that there must be this, let's say, fig arc. And if we look at the data, then actually place order happened 100 times with on average 5 items being involved. And I could do this for the rest. If we do that, we get the diagrams that we just saw. So by doing this, we get, let's say, one step closer to data and reality. And these models at first sight may look more complicated, but in the end, this is simpler than having different models looking at the same reality. And of course, on these models, you can do, let's say, again, you can attach sliders to it to seamlessly simplify these models. And you can also look at, let's say, a subset of the object types under consideration. So again, you can make it as simple as you want. So to conclude, in my talk, I started by explaining what is classical process mining. I explained that in reality, it's often very painful to go from a complicated information system with thousands of tables to a simple event log ready to apply process mining. And therefore, I introduced this notion of an object-centric event log. By taking that as an input, suddenly many things become much more clear and much easier, because using that as an intermediate format, we have these techniques to directly discover object-centric process models, which are more complicated. Or we can do this on-demand extraction, where we have, let's say, traditional process models corresponding to the different views without going back to the original information system. If you think this is interesting, there are a few papers. This is let's say, a hot research topic. I think the top paper that you see here matches most closely what I've been talking about. That describes a technique to automatically discover these object-centric process models from the data that I indicated. So if you would like to find more information, I would recommend taking a look at these papers. If process mining is relatively new to you, I would like to point out the process mining book. Also, the chapter on data extraction in the process mining book is already, let's say, showing that this is a problem. It doesn't provide a solution yet, because that is the result of more recent research. There is also the well-known Coursera online course that you can take for free to learn more about process mining. Thank you very much.